It's 2 now, so let's begin the session again. So the first talk is going to be presented by Jun Inoue on Sundials, interfacing numerical solvers, interfacing with numerical solvers.
Okay. Thank you. So this is basically a tool presentation about our OCaml interface to a numerical solver called Sundials. The motivation for this work was modeling hybrid systems. So a hybrid system typically is a controller embedded inside a physical environment. So this shows a model of a controller attached to a boiler. It monitors temperature readings from the boiler, and it turns the boiler on and off. So it interacts with the physics governing the boiler. To build models like this, there are industrial tools like Simulink and Modelica, and there are also a lot of academic ones like Zealous, Ptolemy, Hydra, Acme, and so on. Zealous is the one that we were working on. Now, one of the most basic functionalities of these tools is to simulate the whole system, including the physics. So you get plots like the one below. And to do this, you need to hook up with a numerical solver. The solver that we hooked up to is called Sundials, and it's a suite of 6 numerical solvers from Lawrence Livermore National Labs. It can solve ordinary differential equations, or ODEs, algebraic differential equations, differential algebraic equations, or DAEs, and nonlinear non-differential equations. It's a very feature-rich library with multiple options for parallelizations by MPI or OpenMP or pthreads. It also features things like sensitivity analysis, which tells you how sensitive your model is to certain parameters in the model. And it's one of the most widely used state-of-the-art numerical solvers. But unfortunately, if you want to use this solver from C, it looks like that. And I don't expect you to read that, obviously, but what this is doing is after allocating some data structures and initializing it, it's calling a bunch of functions to set options in the solver, like which algorithm to use. And these functions calls are interdependent, so that if you screw up the ordering in which you call these functions, or if you forget to call functions that you were supposed to call, you get either an error return value or a seg fault. So it's very C, it's very error prone, it's very dangerous. And what we provide with you is a better alternative that looks like this in OCaml. So again, I don't expect you to read this, but the point here is that the configuration is now done with ADTs. So instead of calling a bunch of functions, you build up an ADT that specifies the options that I want. So here I'm saying use Newton iteration, but this Newton constructor takes an argument, so that I have to supply an argument that specifies an auxiliary algorithm that the Newton iteration is going to use. So in this way, the type system is forcing you to come up with the right combinations that make sense for the solver. Okay, so this is about a OCaml interface to Sundials, but this is not just a function for function, type for type translation of the underlying library. It's an API that's done in the right OCaml kind of way. Okay, and it supports all documented features in this library with a modest overhead, with in most cases we're less than 70% overhead, and in many cases it's even less than 30%. And in this talk, I would like to give you a general overview of how the library works and show you some benchmark results. So I'll start with a quick demo. Okay, and again, the point here is not to understand all the details, because there's a lot of stuff in it, but I'd like you to just get the flavor of what it's like to program against this library. So here I would like to solve a trivial ordinary differential equation that looks like this. It's y prime equals 1. So I want to find a function y that depends on a variable t, whose derivative is constantly 1. Okay, very simple. And to solve this kind of problem with Sundials, you first create a callback that specifies this problem. The type of the callback looks like that, and the real array.t type mentioned here is just an alias of the big array type. So I'm going to dump the module, real array module here, and that's the definition of real array.t. So it's just an alias for a one-dimensional big array that holds 64-bit floating point values. Okay, so the task of this user-defined callback function is, given the current value of t, the independent variable, and the current value of y, the dependent variable, where t is just one floating point value and y is a vector of such values, to fill in another vector representing the current value of y prime. So here the derivative is just constantly 1, so I just assign 1. Now, if any of you is not interested in following the mathematics, that's fine. All you need to understand is that I define a callback function that manipulates big arrays that are passed in from the interface. Okay, so now that I've set up the problem, I need to give it an initial value. So to solve an ODE, I need to specify the initial conditions. And so here I'm creating the initial vector. The real array.ofList takes in a list of floating point values and converts that into a vector. So the converted vector just looks just like that. So it's just a vector of one value, which is 0, and its type is real array.t, which is just a synonym for big arrays. Okay, but unfortunately, I can't directly pass this into the Sundials library because the C library doesn't understand big arrays. It knows nothing about OCaml. So we need to wrap it inside a little bit of fluff to let it know how to access the contents. And that's what this line is doing. So this nVectorSerial.wrap function wraps the vector inside some stuff to make sure that the underlying C library can access it. And the wrapped array looks like that. It's almost exactly the same. It's got the same contents, but with a different type called nVectorSerial.t. It's an opaque type that represents the type of the vector that the underlying C library understands. Okay. So now that I've set things up, I can now solve. So I have a function doSolve that initializes the library, and it gives a bunch of parameters specifying the algorithms and the tolerances, which we're not interested in right now. And most importantly, it passes in the callback function that we defined. So this defines the problem, the differential equation that it's supposed to solve. And then I give it the initial values. Okay, and the important thing here is that the initial value is given by the y vector that I created, but I can't pass in the y, the big array that I created. I need to pass in the wrapped version of that array. Okay, and then I'm going to iterate a loop and ask for the value of the dependent variable at various values of t. And again, I won't get into the details, but the important thing is here I'm saying please place the result in this vector, and again the vector is passed in as the wrapped version, not the raw big array that we're manipulating from the OCaml side. Okay, so now if I call that function, what I get is this. So as you'd expect, it would just say that the solution is y of t equals t. So just a quick recap. The important thing is you specify the problems using this callback function that manipulates big arrays. But when you pass in big arrays to the solver, you pass it in this wrapped form. And I'd like to explain a little bit more about what's going on under the hoods when you do this wrapping. Okay, so in the Sundials library, the C library, the vector is represented with a very simple structure that looks like this. There's a C struct named nVector, which has a bunch of administrative data attached to a pointer, the contents pointer, which points to the array of doubles that backs the vector. Now, how is this represented in OCaml? Well, in the OCaml program, we started with the payload, the big array, that has the header somewhere inside the OCaml heap. and the header points to some array of doubles living somewhere in the C heap, okay? So that's the big array that we started with, and when we wrap the big array, this is the structure that was created. So here, we have the OCaml side representation of the n vector, the opaque type n vector dot t. Previously, in the demo, it was called n vector serial dot t. It's opaque, but internally, it's a tuple. The first component of the tuple points to the payload, the big array that we started with. And the second component points to the C representation of the vector that the library understands. So it's just the same administrative data attached to a contents pointer, which points to the storage backing the big array. But unlike an ordinary vector, we secretly allocate one more object behind the n vector structure. And we use this word to store a link back to the OCaml payload, the big array. Okay, and we register this backlink as a GC root so that as long as this structure is alive, so is this payload. So now, when we call into the Sundials library, we passed in the wrapped version of the vector. So that's passing in this part of the structure. And what the FFI does is then it follows this link to get at the C view of the vector. And so it gets that pointer. And then the C library is then happy to manipulate this part of the structure, because this part of the structure looks exactly like any other n vector that the C library would create for itself. So, but now when it's time to call back to the user-defined function that we defined in OCaml, the C library will try to call the function with a pointer to this structure, because that's the only structure that the C library understands. But now, the FFI, given a pointer to this, the FFI knows that there is an extra word behind the structure, so it will look at the backlink and follow this link to get at the OCaml view of the contents, the payload. So now when the FFI calls this user-defined callback, the vector arrives as this payload, the big array. So overall, this representation gives you a unit time conversion for back and forth when you pass something into the Sundials library from OCaml, or when the Sundials library wants to pass something into the OCaml. Either way, it's a unit time conversion consisting of just following one pointer. And notice I also made no assumptions about the type of the payload. So there's nothing that prevents me from change. So I drew this payload as if it's just one big array, but there's nothing to prevent me from attaching, say, an MPI communicator to this, so that if I want to parallelize a distributed vector, I can just store the local portion of the vector and an MPI communicator, so that different processes have different fragments of the vector, and they communicate with the MPI communicator. So in this way, we support different kinds of parallelization with the same interface and with an efficient conversion that involves no copying or allocation when you call back and forth between OCaml and C. So, benchmarks. Sundials comes with 56 examples that model small but meaningful systems. They model things like the population increase-decrease in a food web or food chain, and certain kinds of mechanical systems, chemical kinetics, heat transfer equations, and things like that. We re-implemented these examples in OCaml and compared their running times to C. And these examples are examples, so they're relatively small. The vector sizes range from 2 to a little bit under 1,000. So in these examples, this user-defined callback function spends relatively little time. So any time that's spent doing OCaml-related stuff is mostly spent inside the FFI in our binding. So this benchmark we expect to be relatively harsh on the FFI. So this gives you a kind of a lower bound on the performance. And these are the results. So Oh. Oh. Okay. Whoa. Okay, so it doesn't quite work, so I'll just tell you what the graph looks like. I think that's not gonna work. Okay, so the benchmark looks kind of like that. Okay. Okay, the results are basically that we compared we plotted the OCaml time divided by the C time, and what we see is that in most cases, in almost all cases, if we turn off array bounds checking, the OCaml version takes no more than, in fact, way less than twice the time of C. So in fact, in most cases, it runs with about with no more than 70% overhead, and in the majority of cases, it runs with 30% overhead or less. And there was an outlier where the performance was as bad as 7.6 times the value of C, but in that example, there were some funny things going on that could be overcome by increasing the heap size, the OCaml heap size. So if we increase the heap size, the 7.6 times example drops down to 1.8. So in general, we have a fairly good, whoa, okay. We have a fairly low overhead overall. So in conclusion, so we built a comprehensive interface to this sophisticated numerical solver library called Sundials. It supports all the documented features, and it amounts to about 31 kilolines of code, so it's not huge, but it's a fairly sizable library. The overhead is relatively small. It's like 70% in most cases and 30% in the majority of cases. If you turn on array bounds checking, what you see is that in some of the examples, it goes up to about twice the time of C. With what we realize this performance by having this clever vector representation that involves no copying or allocation when you convert back and forth between OCaml and C views of the data. And we've already started using this solver as a backend to the Zealous compiler, and as just an attestation to its performance, we're not seeing any problems. So it's hard to quantify how good it is because we don't have a baseline to compare against, but we can say that it's doing fine. Okay, it's a little bit early, but that's where you can get the library. It's also on OPAM. So thank you for listening.
Questions? Gabriel?
You say you have a good performance because you have 30% overhead in the majority of cases, but in many problem domains, 30% is quite a lot for a binding. But you would expect the overhead to be 0 or 1%. So what makes this problem different in this respect? Maybe the simples are actually very, very short-running in that function.
So it depends on your expectations, right? So we have this binding that's calling through the FFI in a very tight loop. So the expectation should be fairly low, right? You're mixing OCaml and C in a way that really stresses this this interface, and we were expecting something like 3 times, 5 times slowdown. And in fact, other people we've talked to who tried writing similar bindings for the same library were saying that yes, in several places they're getting serious performance problems, but we don't have that here. So by that token, it's an acceptable performance, at least in our expectations.
So you're running a tight loop, you know, on the OCaml side, you have plenty of shortcuts to this library, the solver library.
What do you mean shortcode?
I mean, you make a lot of calls that terminate quickly.
Yes.
I think there's only for benchmark.
So in the benchmarks, the callback, the called OCaml function spends relatively little time. And so most of the overhead is coming directly from the FFI itself. So with that kind of benchmark, we get 30%, 70%. So if you have a function that spends more time in the OCaml callback, you're more bound by how much slower OCaml is compared to C for crunching numbers.
That might also be the 40% boundary.
Yes, that might also be in that kind of range.
There was a question in the back. Yep.
So, did you make an interface by hand or?
In this case, we opted to make the interface by hand because we wanted to have tight control over the representation, how exactly the calls happen. But yeah, we did think of using interface generators, we just didn't.
Like
Sorry?
Swig?
A what?
Could you
Swig.
swig?
Swig, yes, that's one of the options we looked at, but we decided let's not try to learn something if we can get away without it.
All right. No question? Are there any other? Oh, there's one.
Are these interfaces monadic or?
No, this is in OCaml, so there's no real reason to use monads.
Any other questions? All right. In that case, let's thank the speaker again.